Chemistry 223, and today we're going to talk about the Nernst equation, finishing up our Gibbs free energy and the energy of the cell potential. And then we're going to go into nuclear reactions, nuclear decay rates, and if we can, get into even some carbon dating and other fun things like that. As always, I'm going to start off with posting a few links in the chat. These are links to the Learning Center's website as well as their Facebook and Instagram page. So definitely check them out if you get a chance. There's the website. Following it is the Learning Center's Facebook and website, or Facebook and Instagram. So definitely check them out. Follow them on Facebook and Instagram. Go to their Learning Center or just sign on to Penji and you can schedule a session with one of our tutors. You can also check out our academic coaching that we have here to help you kind of navigate the wonderful world of academia. All right, let's get started now talking about the Nernst equation. Let me plug my iPad in here. There we are. So the Nernst equation, last week we talked about how the relationship between Gibbs free energy and the cell potential, and how if Gibbs free energy is a negative value, it's going to be a spontaneous reaction, and if the cell potential is a positive value, it's going to be a spontaneous reaction. But those are always kind of at these ideal concentrations and equilibrium states. If we can see then how the free energy is dependent on the composition of that reaction material, what's reacting and what the concentration is for these. And we can relate that through that idea of Q. So if we write down delta G is equal to G plus RT ln of Q, we can see then this is kind of the general relationship between those. So depending on what that value of Q is, the Gibbs free energy, the change in Gibbs free energy is apparent there. I think this might be a delta. And we can rewrite that in terms of cell potential. Where the cell potential is equal to that same E of the cell minus RT over NF, where R is the gas constant, T is the temperature in Kelvin, N is the number of moles, and F is going to be the Faraday constant. We're going to multiply that by ln of Q. And since if we don't want to work in the natural log, we can convert that using probably change of base formula and stuff like that to a base 10 log. And the base 10 log gives us this extra factor in there. So I can rewrite this whole thing. Minus, and I'm going to actually combine the ideal gas law, our temperature, which is always going to be at room temperature 25C or 298.15 Kelvin, and divided by the Faraday constant, and then multiplied by this factor, which is 2.303, and it ends up being 0.0592 in volts divided by our number of moles times log of Q. And again, this value here I got by, I'll rewrite it up here. That's equal to the gas constant times the temperature divided by Faraday constant times 2.303. So we can use this equation now to solve for Gibbs free energy if we have a mixture that's not at equilibrium. So let's try that out. Here I have an equation. It's written in kind of cell notation. If we remember, we talked about that a couple of weeks ago. This always starts out with the anode on the left side and kind of works its way to the cathode on the right side, starting out with their neutral forms and what they change into, and it talks about their concentrations in the middle as well. So if we were to write this out, the half reactions, the anode, which is the oxidation, would be the aluminum solid will produce aluminum 3 plus 3 electrons. If we write out the cathode, we can see that's going to be a reduction. And there we have the copper 2 plus 2 electrons will produce copper solid. And when we go to balance these half reactions, we're going to see that there's a different number of electrons on both of those reactions. So we need to multiply each of those reactions by something. So we would multiply this by 2. We multiply that cathode half reaction by 3. And if we did that, then we'll see there's 6 electrons on the product side and 6 electrons on the reactant side. So that gets us the right number of electrons in there. So right there, that'll tell us, because we need to calculate for this, N, Q, and the cell potential E. N is going to equal 6, because there's a total of 6 moles of electrons being transferred in this reaction. So now we have to look up what is the cell potential for both these half reactions. And if you remember, we can find out the cell potential of the total by subtracting the cathode, the E of the cathode, minus the E of the anode. So in this case, let's go find out what those are. I'm going to go to the textbook here. Switch it over so you can watch me. Go to the browser. There we are. And so in the textbook, Appendix L has the standard electrode half cell potentials. And listing those out, we're looking for aluminum and copper. So going down, here's copper. There's 2 of them there. There's actually 3. I'm not worried about that third one. But 2 of them with copper 2 plus. And right now we're going to copper solid, so we want the second one I have highlighted at 0.34. So this is going to be 0.34 volts. Let's go down and find aluminum. I might have passed it because I think these are alphabetical. I didn't highlight it. Here's the problem. There it is there. Negative 1.62 or 662. That's negative 1.662. Which means this is going to be equal to 0.34 volts minus a negative 1.662. And we can figure out what that is. 0.34 minus, parenthesis, a negative 1.662 volts. That's going to be a 2.002. volts. So there's our cell potential. So we've gotten that one. We found that, so we can find our Q value now. Just looking for our Q. Well, we know that the Q is going to be the concentration of the reaction, or the products divided by the concentration of the reactants. Oops. Switch back to my iPad there. So you can see I added up those values there and found our cell potential. So Q is going to equal the concentration of the products divided by the concentration of reactants. Which in this case they give us here and there. So we can see that that concentration is 0.15 divided by 0.025. And I know that the aluminum 3 plus is the product because it's being oxidized, right? So when we write this left to right, we're going to start out with that aluminum solid on the left side, reactant side, and it's going to turn into aluminum 3 plus on the product side. If we write that, so that's our Q value, which is going to be 0.15 divided by 0.025, which is equal to 6. We can see based on this positive spontaneous reaction, or positive voltage, that it will be a spontaneous reaction. Let's try another problem. This one has to do with zinc solid turning into zinc 2 plus on both sides of the equation. In this case, the molarity is really what's changing here. It's going from aqueous 0.1 molar to aqueous 0.5 molar. So let's write these out. Now the anode, in this case, is going to be, again, it's the oxidation. That's going to be the zinc solid producing zinc 2 plus aqueous plus 2 electrons. The cathode is going to be the zinc 2 plus 2 electrons producing zinc solid. And this overall reaction, if we were to kind of break it down, we can see that we're going to have basically be canceling everything out. So we can actually write this in a somewhat different way, putting in the molarity of things. So I can say this is 0.10 molar is what the anode side is going to be. And over here, I can say this is 0.50 molar. Make that look pretty. So by putting those molarities in, when we go to cancel them out, we don't actually cancel the 0, 2 plus, but we can cancel out these and those. And our overall reaction is zinc 2 plus 0.50 molar producing zinc 2 plus 0.10 molar. And all of it's aqueous. So if we looked at what those cell potentials are, looking at zinc, well, zinc 2 plus to zinc is going to be, this has an E equal to negative 0.7618. And I'm seeing that there. Switch over. You can see that in my browser window, just right here. I'll highlight it. If it lets me. So that's the zinc 2 plus to zinc. Zoom in a little bit. And that's going to be a negative 7.618. So that's what I'm going to put on there. And they're both going to be the same in this case. That should be a negative value. So in this case, we don't want to be using just our standard energy of the cell. We need to substitute in that Nernst equation. So doing that, we can see that the cell is going to be equal. In this case, we can see that our normal cell value here is going to be negative 0.7618 minus a negative 0.7618, which is equal to 0. So this is going to be our what we plug into our Nernst equation. Then we can subtract from that, again, 0.0592 volts. That's just our constant values converted to a new constant, divided by 2, the moles of the electrons that are being transferred. We then multiply that by the log of the ratio of those concentrations, 0.10 divided by 0.50. And again, the product is always going to be on the top there. So let's see what this is equal to. So I'm going to leave off the 0 in the front because it's just equal to 0 and put a negative 0.0592 divided by 2 times logarithm of 0.1 divided by 0.5. And this is equal to 2.07 times 10 to the negative 2, which is basically 0.0207 volts. And sig figs probably round to 2 significant figures. The only thing that we really have, this is 0, and these are constants, basically, or integers. So these here are molarities. They're the only things that actually have significant figures. So I'm going to follow those for my sig figs. And that's our solution. That's going to be the energy of the cell for that potential at that concentration, when those concentrations are changing. So let's get into nuclear reactions. I find these a lot of fun. There's a lot of different types of nuclear reactions that we can talk about. I have a nice table here, which are lists of them. There's the, so I should start off, I'm going to write down here. The idea, just a refresher of kind of the notation of the periodic table, is usually we would have, I'm going to use helium as an example to begin with. And you can put its total mass up on the top. So in this case, helium has a mass of 1 with a single proton in it. So the top number up there, it's usually, I'll just say some X values for whatever chemical we have. We have a higher up number on the left-hand side. That tells you the total combined number of neutrons and protons. While the number on the bottom, we denote as Z, is the total number of protons alone. So if you ever had to want to find out how many neutrons, it's just A minus Z would equal the number of neutrons. And the neutrons can change in an atom a lot, where if a proton changes, it actually changes to a different element on the periodic table. So these elements can decay and change and release different forms of radiation. So when that happens, I'm going to go through some of the different forms here. We have the alpha decay. Alpha decay is when you have this atom and it releases a helium atom, helium-4. We call that an alpha particle. It's an alpha particle. And notice that when it releases, the compound, the element that's actually produced, has 2 less protons and 2 less protons and 2 less neutrons. So we reduce the A value, that top number, by 4 and the Z value by 2. So whatever element we started out with, we can go 2 elements down on the periodic table to find out what our product is. For beta decay, we take our initial unstable element, and that releases a beta particle, which is also known as an electron. Beta particles are negative, and we can see that the electron here is denoted by a lowercase e with a -1 in the Z state. So it's really just saying that it has a charge of -1. Normally that's for the protons, and protons are positively charged. So we just put that there. And we said that the mass of the electron is essentially zero, because relative to the mass of the protons and all the nuclei, it has an insignificant level of mass. So when this electron is freed from the nucleus, it produces, it's basically turning a neutron into a proton. So we have one more proton than we would have had before, but the same number of nuclei. So our A value is unchanged, as you can see on the right hand side there. And you can see this is the neutron here, spat out an electron and became a proton. Here the neutrons are white little balls and the green balls are protons. The form of gamma decay that we can have, gamma is really a type of light. It's a very, very high energy light beam. It's so high energy that if there's a gamma ray coming anywhere near you, you need to duck, dodge, get as far away from it as you possibly can. Because it's very radioactive, it's very energetic, and it'll penetrate through just about everything we can think of. And it'll destroy human tissue too. So when this type of radioactive element is happening, we want to stay far away from it. And when that produces, we see gamma has no protons, no neutrons, no electrons, no charge. It's light, it's massless. So we call that with a gamma with a 0 and a 0. Therefore, the new particle is basically unchanged, but it's releasing some gamma radiation in the process. The positron emission we see here, it's basically, we can also call this a beta plus particle. Positrons are just positively charged electrons. So for every form of matter in the fundamental particles, there's an equivalent antimatter that has the opposite charge and the same mass. In this case, the positron is that antimatter to an electron. Electrons have the mass that they do. They're a fundamental particle as far as we know, and they have a charge of -1. Or they have a fundamental charge. It's like 1.6 times 10 to the -19 coulombs, but we call that kind of a -1 electron charge, where the proton has that +1 counterbalance usually. The positron has that same equivalent magnitude of charge, but in the positive direction, where the electron is negative. And it also has the same mass as the electron. So in this case, we start out with this, the element that we're talking about, this unstable nuclei, and we emit a beta particle, which has no mass, we see on the top, but it does reduce the number of protons, because what's happening is a proton, in this case, is turning into a neutron. And it releases this positive charge, becoming neutrally charged. That's a little different than the beta decay, where we had a neutron, which was releasing a negative charge. And by releasing that negative charge, it had to become more positive. Because we have this balance of charge, this conservation of charge that was going on. Looking at electron capture, this is similar to electron or beta decay, but now instead of releasing an electron, it's capturing an electron. It's catching it. So when that happens, you see that the protons go down. And here we see it captures it, and the proton turns into a neutron, and by capturing that electron. And during that capturing of that electron, it produces an X-ray. And that's really a byproduct of one of the fundamental things that happen with electrons. If you accelerate or decelerate an electron, it produces X-rays. It's really a cool phenomenon. And we see that a lot in how we generate X-rays in general. But anytime we have an electron capture, it's going to grab onto an electron, absorb it into the nucleus, turn a proton into a neutron, and a byproduct of that is going to be some X-rays. And since it's turned a proton into a neutron, the proton count, our Z number, is going to decrease by 1. But since we have the same number of nuclei in the nucleus, that A number is not changed. So here's a few tips on balancing nuclear reactions. We can say that the sum of the mass number which is A, of the reactants equals the sum of the mass number of the products. So the sum of the mass number of the reactants is equal to the sum of the mass number of the products. And that's that A value, excuse me, on the top on the left side. That mass number is essentially being conserved. We're not losing any mass, any significant level of mass. Sometimes, generally speaking, we are turning a little bit of mass into energy, but it's such a small amount, it's insignificant when it comes down to things. It's less than the mass of an electron. So we just ignore it, and we think of it as mass is always conserved. So that number should stay the same. The second step is the sum of the charges of the reactants equals the sum of the charges of the products. So now we're talking about charge, and it's just this conservation of charge. Whatever charge we had in that atom to begin with has to equal the combined charges that we have on the other side. So if we're radiating out electrons and we're becoming more positive in that process, the net charge of both the reactant and the product side needs to be the same. And remember that protons and positrons have a positive charge. Same with alpha particles. They have a positive charge to them. Really, we're actually losing 2 protons in that process is part of what we want to think about. So we're losing that 2 plus. Electrons, beta particles, which are electrons, and so on, they are negatively charged. And they're going to usually result in a change, causing something to be more positive. And it matters on what side that electron is on. We saw up here in the beta decay, by producing an electron, it made that Z be a +1. But down here with the electron capture, since it's grabbing onto an electron, the new element is a Z -1. So it depends on where that electron is going. Is it going into the atom? In which case the resulting new element is going to have a Z -1 because we've just turned a proton into the neutron. Versus the beta decay, when the electron is leaving an atom. So in that case, it's turning a neutron into a proton. So those are the steps on kind of how to balance these nuclear reactions. And we're going to give a few of these a try here. First, we're going to look at a reaction of an alpha particle with magnesium-25, which produces a proton and a nuclide of another element. We want to identify that nuclei. So just doing this, we want to kind of work through this word problem. I'm going to underline some of the key elements. It's in a reaction of an alpha particle with magnesium. And it produces a proton. I'm going to write a little arrow over produces. And a nuclide of another element. So I can write this out as kind of like an unknown. We're putting in the values I do know and listing the values I don't. I know there's an alpha particle. Alpha particle is a helium-4. So helium has 2 protons and then 2 neutrons, giving it a mass of 4. I know that's reacting with magnesium. Magnesium is Mg, and they even tell us here it's 2512. So magnesium 25, it has 12 protons in its nucleus. And that's producing a proton. So a proton is just a single helium atom, or sorry, hydrogen atom. Right. So that has one proton in there, and it has zero, or it has just that one proton, zero neutrons in it. So it has a 1-1 for A and Z, plus some other element. I'm going to call that Y. And we don't know what that is just yet. But we know that we have to have that conservation of mass and that conservation of charge. So in this case, what I'm going to do is I'm going to add up the A values, do the summation of A values, and do the summation of Z values. So on the left-hand side, I say this is going to equal 4 plus 25. On the right-hand side, that's going to equal 1 plus A. I know these have to equal each other. So that means that, well, 4 plus 25 is 29. And that needs to equal 1 plus A. So I can subtract 1 from each side. That's 28 is equal to A. And that should give me the right A value for things. So what is the Z? We do the same thing for the Z. That's 2 plus 12 on the left side. On the product side, we're going to have 1 plus Z. 2 plus 12 is 14, which is equal to 1 plus Z. That's 13 equals Z. So now I can write this as some element that has 28, as a mass of 28, and 13 protons. Well, 13 protons, that's an element. We know. We can look at our periodic table. I'm going to go back to my browser, hop over to a periodic table, and we can see, oh, that's aluminum. Can't see my cursor, but that's aluminum there, which is element 13. So we can see that this is really 28, 13 aluminum. Oops. There we go. So we can see it's 28, 13 aluminum, or aluminum 28. Let's try a different one. This nuclide is iodide, and it's iodide 125. So this is going to combine with an electron and produce a new nucleus and no other massive particles. So we know it has to do with an electron. We know it has to do with iodide 125. And we know there's an electron involved. If we look back at our table there of what we had here, we had two that dealt with an electron, the beta decay and the electron capture. And here it says it combines with an electron and produces a nucleus and no other massive particles. Well, if we look on the beta decay, one of the massive particles that's being produced is that electron. So, and the fact that it says that this is combining with an electron means that the electron is going to be on the reactant side. So this is going to be an electron capture. And we can already see, based on the formula we have here, our Z value is going to be reduced by 1. And our A value is not going to change. So that means this plus an electron, which is a -1, 0, is going to produce some value. Well, we know that A is not going to change. That's going to be 125. We know that my 53 is going to be reduced by 1 to 52. And looking at our periodic table, we can look for 52. I see it there, tellurium, Te. So right here on group 16, can't see my cursor, but I can zoom into it. So number 52 is Te. And there we go. So a lot of these are pretty simple to go through. It's the hardest part is identifying what type of reaction you have. Once you do that, it's just how many Z do I add or subtract, how many A do I add or subtract, making sure everything is balanced on the mass and the charge side. So now we can go into radioactive decay. This is kind of it's a similar process, but radioactive decay is the spontaneous change of unstable nuclide into another. So it's when these reactions that we're talking about here, they happen spontaneously. So, all right. Of And there's some terminology for these. We call the initial unstable nuclide the parent nuclide. And this is the initial unstable nuclide. The product of that, kind of what's being produced as it decays, we call it daughter nuclide. So it's this is the product of decay. So going through this list here, we can see this left-hand side is always going to be the parent. This right-hand side is going to always be the product or the daughter. The daughter nuclide can always be the parent of another one because one reaction can kind of chain reaction down. So, for example, we could have uranium-238 kind of turn into thallium, which can decay down into a different form of uranium and back and forth. So it can eventually, one can decay into another, which can then decay into another. So at every step, basically, the daughter becomes a parent, and it's a next generation of decay, essentially. Looking at some of the examples that we have here, we can use this idea of the rate of decay to determine how long it will take for something to decay or how much of this atom is going to be left after a certain time. And we call that kind of using this half-life idea. And you've dealt with half-lives a little bit before. It's really just that constant of half the life it takes, or half the time it takes for it to decay down to its halfway point. I said that wrong. It's the time it takes for it to decay to its halfway point. So half of its concentration or half of the amount is gone. And we define that. Let me just write half-life. T at 1/2 is equal to the half-life. And there's the other constant or variable that we look at is called a decay constant. Which we usually use the character lambda for. And we say n, which is just the number of nuclei. So however many atoms that we have, nuclei we have in there, or just in general. So if we say we have 15 carbon atoms, or maybe we have Avogadro's number with a nuclei. So we could have 10 to the 23rd up to that point. We could then determine how many of those decayed down based off of the half-life of the formula and the decay constant. There's some equations we can utilize here where the decay constant is equal to the natural log of 2 divided by the half-life. And we can rearrange that if we wanted to solve for the half-life. Because sometimes we know the half-life, sometimes we know the decay constant, but there's an inverse proportionality to them, so we can easily solve from one to the other. And since we know that that decay is going to be like an exponential decay, we can say that the number of particles left at any time t is equal to the initial number of particles times e to the power of negative lambda t, where lambda is that decay constant, t is the time that's passed. And t could be in any units of time. It could be days, weeks, seconds. It varies depending on the compound or element we're talking about. And using this relationship, we can kind of plug things in a little bit. We can solve this to find out the time that it would take, which is equal to the negative 1 over the decay rate times the natural log of the ratio nt over no, and not. So the initial, or however many particles we have at time t, divided by the initial number of particles that we had. So we can use these 4 equations to solve for all the different variables we might need to find, depending on whether we want to find out how long it's going to take for something to decay to a certain rate, or what's the half-life of this one, what's the decay rate based off the half-life, and so on. And we're going to give that a try here. So here we have radon 222, and it has a half-life of 3.823 days. They want to know how long will it take a sample of radon 222 with a mass of 0.750 grams to decay into other elements, leaving only 0.1 grams of radon 222 remaining. So here it's telling us the grams here and the grams there. And these are both the grams of radon. Now we can convert these into the number of particles to find n, but we can also look at the idea that the number of particles at any time t, draw that a little bit bigger, at any time t divided by the initial number of particles is going to equal kind of that fraction of whatever's remaining. So where this is the remaining divided by the initial, this should equal the same ratio in grams. So I can say 0.100 grams divided by 0.750 grams is equal to that same value. We can convert those both into numbers, but that conversion is going to be the same, so the equation is the same. So using that to our advantage, we would need to find, we want to find ultimately how long it's going to take for this sample to go down. So looking at our equations back here, that's telling me I want to use this equation to find out t. How long is that going to take? And I just defined what this ratio is here. So I need to figure out what is my decay constant. And they didn't give us that in the equation, but I can solve that knowing the half-life. So I can use those 2 equations now because I have 2 unknown variables. I don't know the decay constant, and I don't know the time it would take to decrease to that point. But I can use these 2 system of equations to solve for those. So let's start off with solving for the decay constant. So lambda is going to equal the natural log of 2 divided by the half-life. Well, the half-life we know is 3.823 days. So we can plug that into our calculator. Natural log of 2 divided by 3.823 days is equal to, say, 0.1813. So that's our decay constant, and I can say this is per day because my days was on the denominator. So that's how fast it decays. Now, using the other equation we had, T is equal to 1 over lambda natural log of the fraction of particles. So rewriting that, T is equal to 1 over lambda, should be the negative, times the natural log of that fraction of particles. I can write that as 0.100 grams divided by 0.750 grams. And I can substitute in for lambda now. This value I found up here, which is 0.1813, and I'll say days. So plugging in these values, negative 1 divided by this value here. I'm going to have to put a parenthesis there. My calculator is going to yell at me. Times the natural log of 0.1 divided by 0.75. That's equal to 11.1 days. So a lot of these problems, they're fairly straightforward as long as you can piece together which equations to use. And then it's just kind of solving for one and substituting it into the other. You're usually going to end up with a system of equations where you have to use kind of one equation, most likely, one of these two, to solve for that. They could give you kind of this equation and tell you, well, we need to solve for t, but that's basically this equation here. If we needed to solve this for lambda, we could do that as well. That's just moving things around a little bit. Just a little bit of algebra. We can solve that for lambda as well, as long as we have the values that we need, the rest of those variables. So remember, anytime you have a system of equations, if you have two system of equations and two unknown variables, you can solve it. The number of unknown variables needs to equal the number of equations you need. So if you have three equations and only three variables and only two equations, you need to find another equation to relate these things, and then you can solve for them. So let's go on and talk about radioactive dating. So radioactive dating is the use of this idea of the half-life of things, focusing usually on carbon dating. So carbon dating is talking about how long it takes for carbon-14 to decay down into carbon-12. Because for carbon, there's different ratios of carbon and different types of carbon. So there is a carbon-14. Let's write that better. Which is 6 protons in it. There's a carbon-13, which has 6 protons in it, and there's a carbon-12, which has 6 protons in it. And the relative abundance of these in the atmosphere or in our planet in general is about 99% carbon-12. And we can see that related in the atomic weight if you look in your periodic table. Let me jump over to here. I'm zoomed in a little bit there. There's carbon, 12.01. So the fact that it's so close to 12 means that a large percentage of that is going to be carbon-12, with about 1% being carbon-13 and a very, very trace amount being carbon-14. And carbon-14 is actually produced when a neutron collides with a nitrogen atom in our upper atmosphere. A little diagram here. So neutrons are floating around in our upper atmosphere as basically it comes down to a cosmic ray breaking up into neutrons and other things like that. But when that neutron collides with nitrogen, which is floating up in our upper atmosphere, it produces a carbon-14. Notice that what's happening there is we're taking one of those protons and we're turning it into a neutron. And we can see that because they both are 14. It's neutron or nitrogen 14 produces carbon 14. And the main difference there is we're gaining an electron there. We're gaining a negative charge, turning a proton into a neutron. So as that happens, that carbon turns into CO2, which is then carbon-14 CO2. And eventually that carbon-14 does um, decay down into carbon-12. But there's a certain percentage and ratio of it in our atmosphere at all times. That ratio also gets breathed in by the plants. It gets breathed in by us and other things. We don't really absorb that CO2, but the plants do. And the plants produce, kind of grow their cellular structure based off of this carbon-14, carbon-12 ratio. And then animals eat the plants, and we eat the plants, and we eat the animals that ate the plants. So now part of us is also composed of this same ratio as well, until eventually everything dies. And as it dies, carbon-14 can then start to decay. Up until then, it can still decay. It's just we're replenishing our body at that constant rate. So we have that constant ratio. So as it starts to decay over time, we can see that that ratio of carbon-14 to carbon-12 is decreased. And we can use that ratio that we find in very, very old objects to determine the average lifespan, because we know what the decay rate is of carbon-12. I really like this diagram. It kind of shows the different percentages. It talks about how the plants absorb the carbon, we absorb the carbon, animals absorb the carbon, and eventually when everything dies, that decay rate starts to decrease. And we can use that decay rate for our advantage. So let's try and utilize this to solve a problem. I'm going to have to write this one out. This is, say we have a tiny piece of paper which is produced from a living plant originally, taken from the Dead Sea Scrolls. And this has an activity of 10.8 disintegrations per minute. Per gram of carbon. This is what we have today. We have this in our hands, well, in a laboratory, in little tweezers, keeping it very safe because it's probably fairly fragile. But we have that today, and we can test to see that it's 10.8 disintegrations per minute per gram of carbon. And we know that the initial activity of carbon-14 is 13.6 disintegrations. Let's just say per minute per gram of carbon. We now want to use this value to find the age of the Dead Sea Scrolls. So we can do that simply by taking this rate that we have. We know the rate that it was and the rate that it's at, and we can use that fraction as inside of our logarithm to solve for it. So remember the equation we used was t is equal to negative 1 over lambda, the natural log of, say, the rate now at time t divided by the initial rate. And if we look up carbon, I need to pull up the right. The textbook has the half-lives of several things in the back of it. And switch that, and you see carbon up here at the top. It's a beta emission, but it has a half-life of 5,730 years. Part of the reason we use it is it's very abundant in our universe, or especially in our planet, and it has a very long half-life. So we can use it to date things that are very, very long. Anything with a very short half-life, it's going to be gone in a matter of seconds, minutes, or days. So if you're looking at something that's tens of thousands of years old, it's really hard to use. If you were looking at something like, I just saw it. This is iron 49 has a 0.08 second half-life. You can't see what I'm highlighting. Yep, there it is. Yeah, 0.08 second half-life. So that's going to basically decay incredibly fast. We're not going to see any of that in a few minutes, let alone a few years or tens of thousands of years. But our carbon, 5,730, is the rate of decay. That's the number of years it is. So going back, we know our lambda is the point. So that's lambda is equal to 5,730 years. So our time is then going to be equal to, or how old this thing is, negative 1 over 5730 years times the natural log of the fraction of these rates. So I can write it as 10.8. That's the rate that it's decaying now, or disintegrating now, divided by 13.6. We can plug that in to our calculator. The negative 1 divided by 5730 times the natural log 10.8 divided by 13.6 gives us 4.023 times 10 to the negative 5. I feel like I did something wrong there. Oh, I did something completely wrong. That's the half-life of it, not lambda. Whoopsie. Ignore those things. It's easy to make a mistake here. This is the half-life. So I have to use that half-life to find lambda, which is the natural log of 2 over that half-life, 5730 years. So let's find that real quick. Natural log of 2 divided by 5730 years. That's 1.21 times 10 to the negative 4. So it's going to be 1.21 times 10 to the negative 4. I'm just going to go back, grab my equation from before, and change this guy. Inserting in 1.2. I should put parentheses. 0.2 times 10 to the power of negative 4. Oh no. Let's write it again. I have an extra parenthesis or something in there. 1.21 times 10 to the power negative 4, close parentheses, times the logarithm of 10.8 divided by 13.6. There we go. That's 1.9. So I'm going to move that decimal place 3 places to the right. So it's going to be 1,905 years. That's how old the Dead Sea Scrolls are. So you can subtract, even if you wanted to. This is 2021 minus 1905. And we can see that those are about 115 years old. No, that was back in 116. The year 116 is when they were made. So about. So that was a long time ago, long before we knew anything about carbon dating and stuff. But that's all we have time for today. Best of luck for you on all of your homework and finals and papers and everything like that. Make sure to make an appointment with tutoring and Pingy if you need any help, and have a great week. Thank you.